Welcome to Algorithm video series. In the previous tutorial, we discussed lower bound problem and we used modified version of binary search algorithm to solve that problem. Today, we will use another version of binary search algorithm to solve lower bound problem. This second version is more simpler and more similar to normal binary search algorithm. Alright, here is the problem statement. Given a sorted list and a target value, find the index of the first element that is greater than or equal to the target. If no such element exists, return size of the list. Here input is a sorted list which can contain duplicate elements and a target value. Output is first position where we can fit target. That is, we want first position where element is greater than or equal to target element. For example, if we take target as 30, here first element is 10. Compare 10 and target element. Here 10 is less than 30, so ignore. Next element is 20. 20 is less than 30. Ignore. Here next element is 20. 20 is less than 30. Ignore. Here next element is 30 and it is equal to target element, that is 30. So this is our output. Here this is the first position where element is equal to target element. We need to find the position where element is equal to or greater than the target element. If our target is 35, then here 10 and 35, 10 is smaller, 20 and 35, 20 is smaller, 20 and 35, 20 is smaller, 30 and 35, 30 is smaller, here also same, here also same, here also same, here 40 and 35, here this element is greater than 35. So this is our output. This is the first position where element is greater than or equal to target element. Here in this example, element is greater than target element. So our aim is to find the first position where element is greater than or equal to target element. Simple, right? To solve this problem, we'll use binary search algorithm, but normal binary search doesn't work here. We need to modify the binary search algorithm. Here we have normal binary search algorithm. In this, first we'll start by defining a search space. That is, we'll take two pointers, low and high. Low will point to the first element of the list and high will point to the last element of the list. Low equal to 0, high equal to length of list minus 1. Then we'll find the middle element. For that we'll use low plus high truncated division 2 formula. Then we'll compare the middle element and the target element. Here there are three possibilities. One is mid element is equal to target element. In that case we'll return the index. And the second scenario is mid element is less than target element. If middle element is less than target element, then we need to search in the right side, right? So we'll take low equal to mid plus 1. Third scenario, mid element is greater than target element. In that case, we need to search in the left side. So high will point to mid minus 1. To change the search space, we'll use low and high pointers. This is the logic behind the normal binary search algorithm. Now, we need to use this binary search algorithm to find the lower bound. If I take target as 30 here, then this is low, this is high. So we'll find the middle element. So middle element is this and target is 30, right? When we compare target and middle element, here target is equal to middle element. In that case, in the normal binary search, we'll return its index, that is 3. So we'll get output as 3. But here, the first position where element is greater than or equal to target element is second position. So we need to get output as 2. But here we'll get output as 3, right? That's why normal binary search doesn't work here. Okay, next, let's see how to modify binary search algorithm to solve lower bound problem. So start by defining your search space. Take low and high pointer. Low equal to 0, high equal to length of list minus 1. Then find the middle element. Low plus high truncated division 2, use the same formula. Then compare middle element and target element. Here we need to consider only two possibilities. Because here we want to find the first position where element is greater than or equal to target element. So here we need to consider only two possibilities. Mid element is less than target and mid element is greater than or equal to target. So when mid element is less than target, if element is less than target, we need to ignore that, right? So here when middle element is less than target, we need to ignore the left side and we need to search in the right side. To search in the right side, we need to take low equal to mid plus 1. Why ignore all the elements in the left side of the middle element? That is because here numbers are sorted in ascending order. If middle element is less than target element, that means all the elements present in the left side is also smaller than the target element. So no need to check them. Simple, right? Next, let's consider next scenario. What if mid element is greater than or equal to target element? Here we want to find the position where element is greater than or equal to target element. When this condition is true, that means we found an element which is greater than or equal to target element. So now we found our answer. So what we can do is we can save that answer. Take a variable, for example answer, then store that index. Now we found our answer, we need to stop, right? No, because here we found a position where element is greater than or equal to target element. But here in the lower bound, we want to find the first position where element is greater than or equal to target element. Here we found a position where element is greater than or equal to target element. Whether this one is the first position, we don't know. So what we need to do is we need to continue search in the left side. To search in the left side, we need to take high equal to mid minus 1. When the middle element is greater than or equal to the target, we store the index because it satisfies the lower bound condition, a element greater than or equal to target element. So it can be one of the possible answer. However, we can't stop here. Binary search doesn't check elements sequentially. Even though we found a position where element is greater than or equal to target, we do not know whether this is the first such position. There might be another element on the left side that is also greater than or equal to target element. Here we need to find the first position where element is greater than or equal to target element, not any position where element is greater than or equal to target element. That's why when we found a position where element is greater than or equal to target element, save that answer, it can be one of the possible answer, and search in the left side. Why left side? Because if I want to search for the first occurrence or first positions, we need to search in the left side because here numbers are sorted in ascending order. So this is the modified version of binary search algorithm to solve lower bound problem. In the previous tutorial, we modified binary search algorithm to solve lower bound problem. We can call it as version 1 and this algorithm as version 2. What is the difference between previous version and this one? Okay, so in the first version, we can call it as boundary method. Instead of storing answer, we shrink the search space until low itself becomes the lower bound. But in the second version, we can call it as store answer method. Here, whenever we find a element which is greater than or equal to target element, we'll store that index as one of the possible answer and move left to check if there is an earlier valid position. First version, in the previous version, we won't take any variable to store the result, but here we'll use a variable to store the result. And in the previous version, initially we'll take high equal to length of list. Here we'll take high equal to length of list minus 1. That is because in the previous version, by setting high equal to length of list, we can handle the case where all elements greater than target element gracefully. But here, this version stores the possible answer in a separate variable. So high only needs to cover actual indices of the list. There is no need to go past the last element because answer handles the case when target element is greater than all other elements in the list. And also stopping condition is also different. Here in the first version, when we have only one element in the search space, we need to stop. But here when low becomes greater than high, we need to stop. This second version is more similar to normal binary search algorithm. Okay, so let's take few examples. First, let's take target as 20 and find the middle element. Here, this is the middle. Compare the middle element and target element. Here, middle element is greater than target element. When we found an element greater than or equal to target, what we need to do is we need to store this index. So take a variable and store this index and search in the left side. So here, high need to point to this side. We can ignore these elements now. This is a search space. Now find the middle element. This is middle element. Compare middle element and target element. Middle element is equal to target element. When element is greater than or equal to target element, save the index and search in the left side. So here answer becomes 1. High equal to mid minus 1. Calculate middle. So here 10 and 20. Here 10 is smaller. Here middle element is less than target element. When middle element is less than target element, we need to search in the right side. So low becomes mid plus 1. Now here you can see low is greater than high. In this binary search algorithm, when low becomes greater than high, we need to stop. So this is our answer. Here we need to find the first position where element is greater than or equal to target element. Here 20 is equal to 20 and it is present at index 1. That is our output. Okay, let me take another example. Let's take 50. Okay, so this is low and this is high. Here you can see 50 is greater than all the elements present in the list, right? Initially what we'll do is we'll take this answer as 8. That is length of list. Then find the middle element. 30 is equal to 50. No, 30 is smaller than 50. If element is less than the target element, search in the right side. Low becomes mid plus 1. This is our search area now. Find the middle element. Compare middle element and target. Here element is less than target element. So search in the right side. Now again find the middle element. Now find the middle element. 30 is less than 50. So search in the right side. Find the middle element. 40 is less than 50. So low becomes mid plus 1. Search in the right side. So now here you can see low is greater than high. So now we need to stop. So we'll return this answer as 8. As I said, in this version, to handle this scenario, when target is greater than all other elements in the list, we'll use this method. Here we use an answer variable to store the possible lower bound index at each step of binary search. We initialize this variable with the default value, that is length of list, because the lower bound represents an insertion position, not necessarily an existing index. If the target is greater than all the elements in the list, then middle element is less than target condition will be true for every mid. In that case, the condition middle element is greater than or equal to target never becomes true. So answer equal to mid is never executed. Without a default value, answer would remain undefined or incorrect. So by initializing answer equal to length of list, we correctly return the position after the last element, which is the valid lower bound. Here, if we didn't initialize answer as length of list, here we saw the statement answer equal to mid never executes. So we won't get proper answer. So that's why initially we need to assign length of list as the default value for this variable. Okay, next example. Target is 25. Initially we'll take this value as 8, that is length of list. Now find the middle element. Compare the middle element 30 and 25. Here 30 is greater than 25. Here we found a position where element is greater than target element. So it can be one of the possible answers. So save the index. Now answer becomes 3. We'll update this variable. Now answer is 3. We need to search in the left side. High is mid minus 1. This is our search area now. Find the middle element. Then compare 20 and 25. Here 20 is smaller. If element is smaller, then search in the right side. So low becomes mid plus 1. Now this is our search area. Find the middle element. Compare 20 and 25. 20 is smaller. So search in the right side. Low becomes mid plus 1. So now here you can see low is greater than high. We need to stop binary search. So this is our answer. Here at index 3, we have an element which is greater than 25 here. That is our target. Okay, next let's write the program. Here we have a normal binary search algorithm. Here you can see the program. Next, let's modify this algorithm. Low equal to 0, high equal to length of numbers minus 1. Low is less than or equal to high. Find middle. And if middle element is equal to target, here we have this condition. We don't want this. We can remove this. Here, if middle element is less than target element, if element is less than target element, then we need to ignore left side. We need to search in the right side. So low equal to mid plus 1. Else, this will execute only when numbers of mid is equal to target or numbers of mid, that is mid element is greater than target element. In this case, we need to store the mid element also. So we'll take answer equal to mid and initially I'll take its value as length of list. To find the length of list, we'll use len. If middle element is less than target element, then I'll take low equal to mid plus 1. Search in the right side. Else, when this else becomes true, when middle element is greater than target or when middle element is equal to target element. What we need to do at that time? We need to store that index first. It can be one of the possible answer. Then we need to search in the left side. Why left side? Because here we want first position where element is greater than or equal to target element. To search for that first position, we need to search in the left side. Next, here we need to return answer. Why answer? Because it will hold a final answer. Then here, this function will return answer. Then we can just print that without using if else. I'll print like this. Lower bound index and result. Save and execute. Be careful about the indentation, okay? Let's enter 5. Lower bound index is at 2. Let me enter 30. So at index 3. If I enter 6, we'll get lower bound index as 5. Okay, so this is how we can solve the lower bound problem using binary search algorithm. So that's it for now, guys. Thank you for watching. Don't forget to subscribe to my channel. I will meet you in next class. Till then, take care.